All right, calculus, we're looking at Unit 5, curve sketching unit lesson 7, and we're going to talk about concavity. So concavity is just described as the way it curves below. So curving downwards, concave down. You could set your ruler on top of the curve there and everything would lie below it. Concave up would be you could sit that ruler underneath the curve and everything would pull away from your ruler upwards at that point. We're going to look at three very familiar functions. We're going to look at x squared, x cubed, and x to the fourth. So we have a rough sketch of x squared, our quadratic. This lumpy smartboard really drives me bonkers. So you draw a nice one, please. We have x cubed, a little sharper, cubic, and x to the fourth. And we're going to look at the first derivative and second derivative, and that can help us relate to the concavity. So for my function, my first derivative would be 2x. And my second derivative is 2. This is always positive. And we can see that this function is always concave up. For my cubic, my first derivative is 3x squared, and my second derivative is 6x. So I have a change of second derivative status here. When the second derivative is 0, that happens when x equals 0. For values when x is greater than 0, 6x is positive. For values less than 0, so when x is negative, my second derivative is negative. At those places, when my second derivative is positive, it is concave up. So it's like you have this dish. As I have negative x values, my second derivative is negative, and that is where it is concave down. X to the fourth, my first derivative is 4x cubed, and my second derivative is 12x squared. Wherever x is positive or negative, this is always greater than 0. It is always concave up, which is what we see. So my second derivative can allow me to check for concavity by whether it is positive or negative. So let's look at the summary from your textbook. If the second derivative is positive at a point, the concavity is upwards. If the second derivative is positive at a critical point, then the critical point is a local minimum. If the second derivative is negative at a point, the graph is concave downwards. An inflection point, this is important, makes the transition from concave up to concave down and vice versa. It will be 0 at an inflection point. So as we change concavity, we're looking for those zeros. Let's sketch y equals x to the 1/3. So for our algorithm from yesterday, we are looking for vertical asymptotes. There aren't any. There are no discontinuities in the domain. But we thought about it. Number 2 was x and y intercepts. When x is 0, y is 0. When y is 0, x is 0. There are no other options for that one. Number 3 and number 4 is my first derivative test. I am looking where my derivative is 0 or undefined. So let's find the derivative of this thing. 1/3 x to the negative 2/3. I could rewrite that as 1/3 cubed root of, well, I could just write it as x to the 2/3. Don't need to complicate it, I suppose. X to the 2/3. All right. This is undefined. At x equals 0. So that is a critical point. We already know that this critical point is 0, 0. So we're going to just set up a nice little table and have a look here. For my x values, I'm going to look about 0 to the left and to the right. My derivative, if I have a negative, where is my derivative? Here it is. So I know that this is undefined. If I look to the left, if I have a negative, I'm going to get a negative. I'm just putting values in here. If my x value is larger than 0, I have a positive root. It'll be positive. So I know I have, oh, sorry, my bad. If I put a negative here, so this one is actually a positive. If I put a negative in there, I'm going to take the cube root, which is negative, but then I square it. So I missed this piece when I was doing it in my head. My bad. So they're both positive. So we are increasing. We are increasing again. So it is not a maximum or a minimum. But it is a critical point. That tells us about our function. Okay. Let's look at the second derivative test. And this looks at concavity. Okay, my second derivative, f double prime, is, okay, I just need to be able to see it, 1 over, oh, I don't like that. Let's write it like that, 1/3 x to the minus 2/3. Okay, my second derivative, bring down the power, negative 2/9 x to the negative 5/3. That is my second derivative. I could rewrite it, I suppose, as negative 2 over 9x to the 5/3. I want to know when that is 0. Or undefined. Well, it is never 0. It is undefined when x is 0. So we have a point of inflection as well at 0. So I'm just going to add to my chart here. I love my chart. F double prime of x. You could do all lines around it, make it beautiful. The point of inflection. So I have point of inflection. Because my derivative, my second derivative is undefined. If I look at negative values, cubed root of a negative, so I'm less than 0. Cubed root of a negative is a negative, and a negative to the power of 5 is still a negative, but the top's negative. So we end up with a positive for x values that are negative. If I put a positive x value in there, I have a positive on the bottom and a negative on the top. So I have concave up, point of inflection, concave down. So that 0, 0 point is really important. It's not a maximum or a minimum because it's increasing both from the left and onto the right, but I have different concavity. So my basic shape is concave up, and you can see that I am increasing as I travel to the right, and concave down, but continuing to increase. So our second derivative test can help us with something that's shaped like that. We should continue. We have concavity, my second derivative test. I should be looking for extremities. So I went ahead and graphed it already, but just let's check our work here. For my extremities, I should be looking at the limit as x approaches infinity for the function. And if I'm taking the cubed root of a huge number, I still get a huge number. So I expect that this will continue to increase as we go. I have no horizontal or oblique asymptotes. I should also have some key points to anchor our work. If I already have 0, but I should look to the right, to the left, and let's do a couple of pretty numbers a little further. Let's say, because I know I've got a cube root of 8 and negative 8. Oops. Let's negative 2 and 2. Okay, so I've already drawn it, but these are good stepping stones in order to graph properly. Let's do one more today. Let's do 1 over x squared plus 3. So let's walk through our steps. Number 1 is we are looking for discontinuities. This one, there are no vertical asymptotes. There are no places where the denominator is 0. I see that you have thought about it. Awesome. Number 2. I am looking for intercepts. My y-intercept would be 1/3. There are no x-intercepts. All right, number 3 and 4. We tend to make the first derivative test, where we look for critical points and decide if they're local max or min. Okay, let's look at the first derivative. I have, well, maybe an easier way to write this, because I am like super lazy. X squared plus 3 to the negative 1. Okay, bring down the negative 1. Decrease the power by 1. Don't forget the guts. There we are. You could rewrite that as negative 2x over x squared plus 3 squared if you like. That's my first derivative. I want to know when it is 0 or when it is undefined. It is 0 at x equals 0. It is not undefined anywhere. So we have a critical point, and the point is actually 0. If I put a 0, it's 0, 1/3. And we already had that one. So that is a critical point. I am going to set up a cute little table. I want to look about 0. So I have 0 because my derivative is 0 there. I want to look to the left and to the right. At the left, if I put a negative value into the derivative, where did it go? I get a positive on the top. I always have a positive on the bottom, so that's going to be positive. If I put a positive value, the top is negative, the bottom is always positive, that's going to be negative. I know I do this quickly, but you're smart. That tells me about the function. It tells me it's increasing. It tells me it's decreasing. So if something is increasing and then decreasing, we have a maximum at our critical point. Okay, and we already know what that point is. That's awesome. The next thing that I should look for is perhaps the second derivative test. Okay, that is my second derivative when it is 0 or undefined. My second derivative, oh no, I have a quotient. So, derivative of the first times the second. Subtract the first. Derivative of the second, bring down the 2. X squared plus 3 to the 1, don't forget the guts. Okay, all over the bottom squared. X squared plus 3 squared squared is to the 4. I'm going to tidy that up by taking out a factor of x squared plus 3 and a factor of 2. I got too many negatives going on here. I'm just going to do, yeah, I'll do a negative. Negative 2. Okay. For the first term, I have another x squared plus 3. For the second term, I have another negative. I have another 2 and an x. Okay, so this one, done, and another 2x. All over x squared plus 3 to the 4. So that becomes a 3. He gets gone. I have negative 2 times. I'm going to tidy that up. X squared subtract 4x squared is negative 3x squared. Positive 3. All over x squared plus 3 cubed. Factor of negative 3. It is entirely possible I got something wrong, but I think I'm good. I want to know when this is undefined or when it's 0. So that second derivative is 0 when x equals 1 or x equals negative 1. It is never undefined. So I am going to set up a similar table for the second derivatives. I am looking about negative 1 and about 1. I'm going to look to the left of negative 1. I'm going to look in between 1 and negative 1. And I'm going to look to the right of 1. This is a test for concavity. I know my second derivative is 0 here and here. I am going to be using that second derivative, as ugly as it is. So if I use a value less than negative 1, so let's say x is, I don't know, negative 2. and I have a negative 2 right here. It's positive, positive, positive on the top. Positive on the bottom is definitely positive. If I put a value in between negative 1 and 1, a really good choice would be 0. So if I put a 0 in there, I have 6 times negative 1, that's negative. The bottom is positive. It's going to be negative. If I put a value greater than 1, so say x was 2, the top would be 6 times 4 subtracting positive. The bottom is positive. It's positive. So I have concave up. The function is concave up. It is concave down. It is concave up again. I have a point of inflection. I have another point of inflection where we have changed concavity. Those points would be really, really helpful. So I have the 0 already, but I'm going to look at those points of inflection as really good key points to have. I have, if I put a 1 in there, up at the original function, which is 1 over x squared plus 3, I have 1 over 4. If I put a negative 1 in there, I also have 1 over 4. So these are our 2 points of inflection, 1 1/4 and negative 1 1/4. 1 1/4, negative 1 1/4, where we're going to change concavity. I also have a maximum, which is my y-intercept at 0 1/3. A little bit higher, so not super well done scale here. All right, so we have our maximum. We are going to look as we look at the extremities. Let's find some space at the bottom here. For our extremities, we are looking for horizontal and oblique asymptotes. So we are looking as x gets really, really big. I am going to look at my function, and I'm going to factor out the largest power. I know there's not an oblique because it's not 1 degree higher. 1 plus 3 over x squared. 3 over x squared gets closer and closer to 0 as x gets really, really large. And in fact, this whole function gets closer and closer to 0 as x approaches infinity. There is no oblique asymptote. 2 reasons. You can't have a horizontal and an oblique asymptote at the same time, nor is the numerator, it is not 1 degree higher than the denominator. So we have our critical point, which is our maximum at 0 1/3. We have points of inflection. Point of inflection as opposed to point of intersection. Inflection, we better put that up there. Point of inflection. And we're going to approach 0 as we get larger in both the positive and negative direction. So funky little thing. Maximum concave down. Concave down. So that's supposed to be smooth. Then we have concave up, getting closer and closer to 0. Concave up, getting closer and closer to 0.